Wave functions. Which of the following wave functions satisfies the wave equation? Y of xt equals a cosine kx plus omega t, y of xt equals a sine kx plus omega t, y of xt equals a parentheses cosine kx plus cosine omega t. And finally, for the wave of part B, which is a sine kx plus omega t, write the equations for the transverse velocity and transverse acceleration of a particle at point x. So let's start with recalling the linear wave equation. So this was a partial differential equation. The second derivative of the wave function with respect to x must be equal to 1 over the propagation speed squared, the second derivative, partial derivative of the wave function with respect to time. So this linear wave equation has solutions of the form y of xt is f of x plus or minus vt, or we can write this as g of kx plus or minus omega t. K is the wave number, 2 pi over the wavelength. Omega is the angular frequency, 2 pi times the frequency. Now, part A, the first wave function we're given is y of xt equals a cosine kx plus omega t. And clearly, this function is of the form f of kx plus omega t. It's a sinusoidal wave which is traveling to the left. So it's traveling in the minus I hat direction. So if we write del y del x, partial derivative with respect to x, this gives us minus a k sine kx plus omega t. The second derivative, del square y del x square, is equal to minus a k square cosine kx plus omega t. Okay, now we need the time derivative. Del y del t. This is minus a omega sine kx plus omega t. And the second derivative with respect to time, del square y del t square, is equal to minus a omega square cosine kx plus omega t. Now I would like to remind you that the propagation speed of a wave is its wavelength times its frequency, or wavelength divided by the period, which can be written as 2 pi f divided by 2 pi over lambda. Therefore, this is omega divided by k, angular frequency to wave number ratio. So if we examine this situation here, second derivative with respect to x, del square y del x square is equal to minus a k square cosine kx plus omega t. Now, is this equal to 1 over v square del square y del t square? So 1 over v square is 1 over omega over k squared. del square y del t square. And this would be k square divided by omega square multiplied with del square y del t square, which we have found to be minus a omega square cosine kx plus omega t. So you can clearly see that these omega squares will cancel and we will be left with minus ka square cosine kx plus omega t. So we find that as a result, by explicit substitution into the linear wave equation, a cosine kx plus omega t satisfies the linear wave equation. All right. Now, part B, we are given y of xt equals a sine kx plus omega t. So this is clearly of the form, once again, f of kx plus omega t. Therefore, it satisfies the linear wave equation. So the difference between sine kx plus omega t and cosine kx plus omega t is just a phase difference. It's basically the same thing, so it satisfies the linear wave equation. Now let's look at the case in part C. We are given a wave function y of xt, a cosine kx plus cosine omega t. So this function is not of the form f of kx plus or minus omega t, but can it be rewritten in this form? So just to be sure, let's check what happens if I substitute it into the linear wave equation. The first derivative, del y del x, is minus ak sine kx. The second derivative, del square y del x square, is minus a k square cosine kx. The time derivative, del y del t, is minus a omega sine omega t. And second derivative, del square y del t square, is minus a omega square cosine omega t. And the propagation speed v is omega divided by k. So as we have mentioned in the previous section, so this is omega divided by k. So if I write 1 over v square del square y del t square, this is basically minus a k square cosine omega t. Now, looking at the second derivative with respect to x, I have minus a k square cosine kx. This is clearly not equal to minus a k square cosine omega t, because kx is not equal to omega t. So I conclude that y of x and t, a cosine kx plus cosine omega t does not satisfy the wave equation. All right. So that's the answer to part C. And part D is asking me about the transverse velocity and transverse acceleration at point x. So this is done for the wave function given in part B, which is a sinusoidal wave traveling to the left, a sine kx plus omega t. The transverse velocity, Vy, at point x is the partial derivative del y del t. This is going to be a omega cosine kx plus omega t at position x, and the transverse acceleration ay is the second derivative del square y del t square, which is minus a omega square sine kx plus omega t. So this basically gives us our final answer. Let's summarize what we did here. We were given a set of wave functions and we were asked to decide which of these satisfy the linear wave equation. And the linear wave equation is second derivative with respect to x is 1 over v squared del square y del t square, which has solutions of the form f of x plus or minus vt. It's minus if the wave is traveling to the right, if it's plus if it's traveling to the left, or in plus I hat and minus I hat direction. We can also write this as g of kx plus or minus omega t. And a cosine kx plus omega t is of the form f of kx plus omega t. So it is a sinusoidal wave traveling to the left. It's not a sine, it's a cosine, so it has a phase difference. And if we substitute this into the wave equation, indeed we find that it satisfies the wave equation. A sine kx plus omega t is similarly a function of the form f of kx plus omega t, a sinusoidal wave traveling to the left. Therefore, it also satisfies the wave equation. The equation given in part C, a cosine kx plus cosine omega t, is not in this form, and actually we find by explicit substitution into the wave equation that the wave equation is not satisfied for this one. And if we take the wave function in part B, the transverse velocity is the partial derivative with respect to time, a omega cosine kx plus omega t at point x, which has a maximum speed a omega, just like the simple harmonic motion. And the transverse acceleration is the second derivative with respect to time, which is minus a omega square sine kx plus omega t, which has a maximum transverse acceleration a omega square that matches the simple harmonic motion. So because the wave propagation is also the simple harmonic motion of the string elements on which the mechanical wave is propagating. So, or the elements of the medium are moving in simple harmonic motion in order to have the propagation of the sinusoidal wave.